hope you have a good lunch. We'll start the next session. It's keynote session 3. Session coordinators are here. Shiranma is there. Kaushik Mondal. Can someone check Kaushik Mondal? Go to the control room and see where is Kaushik Mondal. Okay, so let him come. We can start the session. It's really a privilege today for me that the next keynote session is coordinated by me. The speaker is Professor Icrcicn Kgec. He is my student. He is passed out of 2005 batch at Kgec. In fact, he is my first student. That was my first batch of students who I started teaching. And it's really privilege that I am today not only introducing him, but will try to understand what achievement he has achieved up to now. Okay. Another thing is that Professor Basu has recently been awarded at Shanti Swarup Bhatnagar Award. His schedule was tomorrow, but he is going to Delhi for the presentation award. So I will, without further delay, I would like to call Dr. Hiranma to chair the session. So Dr. Hiranma is an associate professor in the Department of Information Technology at Icrcicn Institute of Information Technology, Kolkata. He earned his PhD in Computer Science and Engineering from Jadavpur University under Professor Debatosh Bhattacharya, focusing on feature extraction for heterogeneous face recognition with over 22 years of academic and research experience. His interests include image processing, computer vision, machine learning, deep learning, AI and quantum computing. He has published 16 SCI index journal papers with a cumulative impact factor exceeding 87 in leading venues such as IEEE TIFF, TIFS, IEEE TPMI, Elsevier Informations, etc. Along with conference paper, book chapters and software copyrights, Dr. Rai has served as co-principal investigator on several national and industry-sponsored projects and currently works on interpretable AI models, human visual system inspired networks, quantum domain image descriptors and AI-enabled solutions for healthcare, agriculture and digital forensics. So I will request Vishita to please felicitate Dr. Hiranma. So I will hand over the session to Hiranma.
Thank you, sir. Thank you for this nice introduction. So we are at the beginning of our last keynote session of today, and we have with us Professor Icrcicn Kgec. Sir already told something about him. Now, it is my privilege to introduce Icrcicn sir. So, Icrcicn sir is an associate professor at the Indian Institute of Science, Bangalore, where he convenes the computer system lab. Icrcicn sir's current research focuses on the GPU's compute stack from the compiler, runtime, device drivers to its microarchitecture. Before moving back to India, Icrcicn sir was researching at AMD Research in Austin, where he contributed to the US Department of Energy's Icrcicn projects, culminating in the development of the Frontier supercomputer, the world's first Icrcicn supercomputer. Icrcicn sir was awarded, sir already told, the Shanti Swarup Bhatnagar Prize this year. He was inducted into the Micro Hall of Fame in 2024 He received the Intel Rising Star Award in 2021 and the Google Faculty Awards in 2021 and 2023. So with this, sir, the stage is yours.
Don't call me sir. Can you hear me? Yes. That's good. So yeah, it's good to be back here after so many years. So today we'll be actually covering some topics that we actually worked in our lab. There's a lot of content. It's okay not to go over it entirely, but I'll actually appreciate if you have any clarification question, feel free to actually stop me. I'll try to actually answer them. If you have any opinion or points, we can actually keep that for the later. Here. So today we'll be talking about the software that runs on the GPU. So GPU, as I guess most of you know, it's the graphics processing unit. But we will not be talking about the graphics software. We will be talking about the computation that actually happens on the GPU. Okay. So now the question is that why you care for that? Now, in today's world, it is no surprise. Everybody knows that we are generating so much of data, right? So what this graph shows is that the amount of data that we are generating is over the year is growing at an exponential rate. For example, every time you actually click a like button or purchase something, that is actually a piece of data that is actually created, and you can get actionable knowledge out of that data. For example, advertising, if you can compute on them. Okay. To process on a massive amount of data, you also require a massive amount of compute. And that's why the GPUs come in handy. So they are particularly good at data parallel computing, which means that you are computing same instruction on multiple different data at the same time. That's what they are designed for. And they have been, of course, they are the backbone for AI ML workloads. But beyond that, they are widely used for graph processing, data warehousing, scientific computing, image processing, and so on. So since a lot of today's software relies on the GPU-based computing, so the quality of that software that runs on the GPU matters a lot. Now you might actually ask, what is meant by quality of the software? So here, I mean two things. One is the reliability of that software. So it is not good enough for a piece of program to, if you run it 100 times, it works 99 times. It works correctly 99 times. It has to actually work 100 out of 100 times. Because one time it actually malfunctions, it can cause disasters. For example, software reliability issues are all over the place. This is hard to actually read probably, but you don't have to read. I think the last one itself, AWS had a big disruption. Once that actually happens, things starting from your basic, the airline, for example, to even the smart beds, everything gets disrupted. So what it means is that a lot of our life today is controlled by the software. And the fact that a lot of today's software actually uses GPU, that quality of the GPU software matters in our life. So we'll be talking about the reliability of that GPU software. The second thing that we'll be talking about is this other aspect, which is how well the software is actually using the hardware. Which means if there are inefficiencies in the programming, then that actually leaves performance on the table, and that actually increases the cost of computing. And it matters a lot because if you look at how much people spend in data centers today, it's like this year it is projected to be $455 billion, out of which most of it is actually, a large chunk of it is actually just the GPU cost. And then there are other costs, hard to read here, but it's it was showing around 11 to 12% of US's total energy goes into data centers. So it is both the hardware cost, but also the running cost, the energy cost, right? So if you use if you write programs that use such a costly hardware inefficiently, which means that you are actually leaving a lot of money on the table. So this is the other aspect that we will be focusing on, depending on how much time we actually have. Okay. So two things. One is the reliability of the software. The second is that even the software, even if the software is reliable, at least is there a lot of noise? By the way, I think I'm actually loud enough. I can actually do it. I can shout, no problem. Doctor, at the back, can you hear me? Yes. Okay, this is better. So in my classes, typically, like so, we at ISC, some of the master classes are pretty big, 80 students and so on. I typically don't use microphones. Anyway, so what we are getting at, like two things, okay? The reliability of the GPU software, and that software, even if it is reliable, it should be using the hardware as efficiently as possible. These are the two things that we'll be talking about. Now, before we get into any of the details, we'll give you a little bit of teaching background. Okay, so the first question that you might actually think that the GPUs, as it's, can you actually close the door? Actually,
Hello.
yeah. Can you not speak here? No. Okay. Fine. What was that? Okay, so you might actually see, so the GPUs as a graphics processing unit. So one might wonder, why you use the GPUs for parallel computing. So I'll give you a little bit of background. So graphics is what? Like they are actually processing on images. So even if you think of videos, this is just a set of images. And what is an image? It is a set of pixels, right? That is what it does. So what the GPU was always originally designed for is to do efficiently process each of these pixels in parallel and doing the same kind of compute on each of those pixels, right? Now around 2007, so the NVIDIA figured out that this kind of architecture is also good for matrix operations. So if you think of these pixels not as pixels anymore, but think of like an element of a matrix, then suddenly the same architecture becomes so good at matrix operation. And then, luckily, I would say to an extent, that this AI/ML thing happened, right? And if you think of the AI/ML, it is almost entirely linear algebra, which means matrix operations. So suddenly, the GPUs became the backbone of the AI/ML based computation. So that's the story of the GPU. Now, of course, I'm actually oversimplifying. It has a lot of things, up its sleeves, like SIMD execution, many hardware context switch, memory coalescing, and so on, which we will not have time to go in. But GPU is you have to think of today is an designed to do data parallel computation. Now, going back to that first topic, right? So why this issue of reliability is important. So in this context, we'll be talking about a particular issue. What happens is that if a particular program fails every time, like for example, there is a segmentation fault and so on, those are very easy to catch. In a production software, they will never get in, right? But the problem happens if there are corner cases where the software fails rarely. Those are the cases where the software testing would likely to miss them, those bugs. And then suddenly you deploy them in the production and something, unluckily some event happens and the software fails and you don't have any clue what really happened. So one such reason is what's called the synchronization bugs. Now, any parallel software needs to synchronize between the threads from time to time. And if there is a mistakes there, then those causes reliability issues. Okay, we'll be talking about Wang-Sun's cases. But before we get into that, one more interesting thing is that, so when we are talking about the GPUs, we are talking about massive level of parallelism. So what it is actually showing on the x-axis is the year of a particular NVIDIA GPU's architecture has been launched. This is the name of the architectures, and the y-axis is the number of parallel threads that a single GPU can have active at a given time. So for example, the latest one can have more than 300,000 threads ready to execute at any given point of time. So why I am talking about this? This is a massive level of parallelism which requires a different types of programming than you would actually use for multi-threaded programming on the CPU. Okay, so it requires a hierarchical model. Okay. So the GPU's hardware also reflects that. So if you open up a GPU, what you will see is that it has something called multiple streaming multiprocessors. Okay. So think of them as like cores of a multi-cores, okay, at a very, very broadly. Okay. If you open up this essence, each of this essence, what you will find is that it has something called a SIMD unit, single instruction multiple data. So it is executing the same instruction but multiple data, but on different data. And it has some shared, amount of caches and so on, memory, like level 1 cache and sketchpad and so on. Now, GPU's programming hierarchy also, reflects the same thing. So it has a group of 32 threads that typically called the WAP, and that gets scheduled on execution on a single SIMD unit. Similarly, a group of threads up to 1024 threads, which means like up to 32 WAPs, that's called the thread block, that gets scheduled on a single streaming multiprocessor. Then finally, you launch a kernel, GPU kernel, that has hundreds and thousands of threads on a single GPU. Okay. Now, the problem is that globally synchronizing across so many hundreds and thousands of threads is actually inefficient. It takes a lot of time. And interestingly, it is also many of the time it is not needed because of how the GPU programs are written. It's structured like a hierarchy. So what happened is that, say, both NVIDIA and AMD, the GPU vendors, they introduced something called scope synchronization primitives. So this is very unique in GPUs. Is not there in the CPUs. Where you can qualify an synchronization operation, like a fence operation or an atomic operation, with a scope, which means only a subset of threads that are part of that scope would see the effect of the synchronization. Okay, so the scope, for example, you can use one thing. If you use a block scope synchronization, then only the threads within the given thread block will see the impact of that synchronization operation. If we wanted to communicate across all threads, then one has to actually use something called a device scope. Now, why you wanted to use that is because of performance. For example, just to actually give you an example of how it actually matters, let us assume that there are two threads. One is blue thread and another is red thread. These are communicating among themselves. Okay. So let us assume that the blue thread is the producer thread and the red thread is the consumer thread. Now, if these two threads are part of the same thread block, then the programming language guarantees that they will be scheduled on the same streaming multiprocessor. If that is the case, then if this particular threads write a data item using a broader device scope, then the data pushed back on the L2 cache, which is not necessary, because if this other thread also uses device code, it will actually get the correct data, but that is not the most efficient. Instead, what it could have done, it could have used a block scope information, block scope synchronization. The data would be pushed to only the L1 cache, but still that should be fine in terms of correctness, because you still both of them are sharing the L1 cache. Now, why you want to use those? Because block scope operation can be much faster than a device scope operation, because it needs to only consider itself within the threads that are part of the same thread block, which can be 21 times faster. However, the problem is if this producer and the consumer threads are part of different thread block, then they can be scheduled on different streaming multiprocessors. It's not always guaranteed, but sometimes it can actually get scheduled on a different streaming multiprocessor. So which means that they will not actually share these local memories like L1 caches and so on. In that case, if the producer actually uses a block scope operation, even if the consumer uses device scope operation, there will be what is called a data race, because this guy would not see the latest data. The consumer would not see the latest data that is produced by the producer thread, the blue thread, right? And this is something that we actually discovered for the first time and reported, that this kind of races can actually happen and in real life. I had an example, but I will not for the it's how it can be pretty subtle for graph algorithms. I'm not getting into the details of that. So, for example, we found how such even the say graph coloring problems and so on, which are actually implemented on the GPUs, sometimes can actually have this scope synchronization problems. I'll skip the details. It's actually pretty detailed. The other thing that we actually observed is that so these GPUs are actually programmed using, typically there are two type of languages that are actually used. The most commonly used is called the CUDA language, okay, from NVIDIA. Now what happens is that over time they keep on introducing new features, and as they introduce new features, they actually create opportunities, or create not opportunities, I should say, create situations where new types of software bugs can actually stream. Okay, and we found several of them. One of them was what's called a new feature that was introduced called IPS, or independent thread scheduling. So what used to happen is that any GPU design that was actually released before 2017, they had a guarantee that all the threads within the same work would execute in lockstep. So as if that after every instruction, there is an implicit barrier. Now what happened was, after 2017, the model was changed, where it became base default, which means that most of the time, the threads in the work, those 32 threads, will execute in lockstep, but not always guaranteed. So which means that the software, our older software, that implicitly relied on that part work guarantee that all threads are executing in the lockstep, can break even when running on a new hardware. So this is something also we actually discovered, and then what we did is that we created a software tool. It's a runtime tool. It's actually open source as well. We call it Icrcicn, that will actually catch those program bugs before they can actually slip into the production software. Any questions so far? Can I ask any clarification question? Yes, go ahead.
So who synchronize these threads? I mean, I have to write the program something where that will synchronize, or is there any inbuilt some software is there already in the NVIDIA or somewhere that can synchronize this?
Yeah. So ultimately, one has to write the software. This is done by the software. So you will ask for, I need a synchronization at this point and so on, which is typically expressed in the terms of two types of instructions: thread fills and atomic instructions. And then there is also a barrier. There are three types. Now, this software can be written by the NVIDIA folks, which is the library, or by anyone else. but it has to be written in programs. Hardware doesn't do anything automatically. Yeah, you had a question? Yes.
Sir, I had actually had an overview about this framework on your profile. Sir, do you think this software is very effective in detecting 100% of the issues in synchronization and race conditions occurring in the GPU? And if yes, sir, is it detected implicitly within the software module itself, or is the output data tested against test variant data, sir? And then the output is calculated?
Yeah, so first of all, no, you cannot even actually guarantee a software is actually bug free unless there is a model checker, but that doesn't actually scale. So what we actually do is that there are types of bugs that we actually catch. There are the new types of bug that was not known before. On that, it catches whatever exists. But there could be other bugs as well, which our tool doesn't actually catch or are not designed to catch.
Is the output, the output produced by the model is tested against standard reinforced output, or is it checked explicitly on the test data itself?
It's a rule based, so there is no. It takes the rules, so there is no way of something missing. It cannot happen. It's actually there's a rule that comes from the language, programming language guarantees, the CUDA language, and that is actually encoded in the tool. So there is no way, that's validated.
Thank you, sir.
So a quick overview of, I will not actually get into details, but what it actually does is that the whole software gets actually the actual GPU program, they get actually instrumented, and then it does tracking on the GPU, what is going wrong or what might be going wrong, and then there is a risk detection logic. Of course, as I was saying, intentionally this font is small because what we are trying to show is that there is a set of rules that it actually checks every access against. So after that, what happens is that once the races are caught, this is the bugs in the program. So you tell the user, the programmer, that exactly what went wrong. Okay, so you can actually say exactly why in the program something might be actually going wrong. There is a race and a bug, and that the programmer can actually fix after that. And I'm not getting into any more details, but also it had a real life impact. So it caught so far what we actually tested when we actually published the paper. There were 12 data races, which are all bugs, synchronization bugs, hard to catch bugs in open source repositories, including 3 in NVIDIA's own libraries. As I was mentioning, NVIDIA has this Ninja program to write those libraries, but their libraries also has bugs. So, and those are actually acknowledged. They actually acknowledge all of those. So, and also you can actually, this software is open source. Anybody can actually try it out. So this is the one type of tool or one type of work that we actually do in our lab, where we try to actually improve the reliability of the GPU software. So while we are actually doing that, we also started working on something called the performance bugs. Okay. So here the program is functionally correct. So it means like the 100% of the time it produces the right output. However, the program may not be utilizing the hardware in the most efficient manner. Okay, so that's what we call the performance bugs. And why it matters? So it is widely known that GPUs, although they are very costly, a single top of the line GPU today will cost like more than $20,000 US. In the cloud, they are often underutilized. So this is a data from Alibaba, which is a big cloud company from China. So what it's showing, this is a CDF, cumulative distribution function. This is the fraction of the GPU that is typically utilized, and this is the fraction of their GPUs in the cluster that are actually utilized. So what it actually shows, really the data, is that nearly 80% of the GPUs are used less than 50% of the time, which means that there is a huge underutilization of the GPUs. Okay, and this is not only the Alibaba, but recently there was a publication from Microsoft Azure. They were also reporting that in their setup as well, typically the GPUs get utilized, less than 50% of the time. Now, the problem is you buy this really expensive hardware and then underutilize them. That's no good, right? So, one of the contributions that we did in this particular work is that we found that one of the reasons for this underutilization could be poorly written software. Poorly in the sense it is functionally correct, but not using the hardware to the best it could. Okay. So that's because of over synchronization or redundant synchronization, where you don't need to actually synchronize between threads for correctness, but you're still doing it. Right? And we also found that this actually happens because often the programmers prioritize functional correctness over the base performance. Okay. So they would end up doing unnecessary synchronization. And some of the times finding those is actually difficult because I'm not going to the code. I have a tendency to go in the code, but this talk I'll just skip the code part. But overall, many of the synchronization operations, if you want to actually get the best performance, the programmer needs to annotate each of these synchronization operations with the quote-unquote right scope, like the right strength of the synchronization, which becomes sometimes tedious or hard to do. Yes. Again, I will not actually get into the details of how subtle this over-synchronization issues could be, but the bottom line is that manually detecting this extra synchronization in the software is actually pretty hard. Sometimes whether a particular synchronization is needed or not depends on how the variable even has been actually allocated. So I'll skip that. Not only that, we've also found that there are cases in the software where there is a redundant synchronization. Not only the extra synchronization, but redundant. Right? So what it means is that there is a performance that is left on the table. Like unnecessarily say some of the threads are waiting for the other, which is not needed for the functional correctness of the program. Okay. So this was also the first time anyone reported that such kind of over-synchronization can happen in the GPU programs. So ultimately what we found in this work was, there are three types of synchronization, over-synchronizations that can actually happen, over and redundant synchronization. And what we then actually did is that we built again a software tool that will actually catch those over-synchronization automatically. And this has also an additional benefit. The benefit is, so as we're talking about writing both functionally correct and efficient GPU programs is pretty hard. So with our tool, what one can actually do is that a programmer can actually write just a functionally correct program. They don't have to worry about over-synchronization. Let them write the program, then run it through our tool, and it will actually then tell you that whatever one is actually leaving the performance on the table. Which is then there is a one level of program, again, a fine-tuning of the program can happen, which can happen automatically. Okay, so that is the name of the tool that we actually created called Scope Advice. And again, it was actually, this particular tool was not so easy to create. It was because things that we actually suggest needs to be correct as well. I will not get into the details, but it has a formal backing while it will actually make sure that any kind of cases they are saying there is over synchronization, it is actually over synchronization. So and ultimately how it actually works, again, in the GPU programs, there is always a CPU part of the program. There is nothing called a pure GPU program. So what we do is that we actually instrument the program, the GPU program on the CPU, then run it on the GPU together. There is both. This is a red kernel which actually runs along with the blue one. Blue one is the actual program, and the red one is actually runs along. This is our tool that runs along with the target programs and finds out the cases of oversynchronization. I'm not getting the details, but ultimately what happens is that what the programmer ultimately gets is that after the program is run with the tool, it actually gets exactly where in the program file number and file name, line number, where this extra synchronization is there in the program. So what it means is that if you remove those oversynchronization, you suddenly get significant performance boost. Okay. And sometimes this is just a one line of performance, line of change in the program, and one can get like 30% performance uplift. Okay. So what you know, and one of the other things that we actually do is in our lab we are very careful about is that not only we build actually tool, we actually show the real life usefulness of this. So this was actually showing like how we caught like 25 oversynchronization that was not known previously, including the one that is in star. These are the libraries from the NVIDIA itself. Why we actually do that multiple times is that we actually show that even if you have Ninja programmers, they will still have performance bugs and so on. So you need an automated tool to catch these issues. Manually detecting it's not possible because it's too subtle. And if you remove this oversynchronization, then what you get performance which can be significant, like 37 to 54% of the performance improvement on these programs, just one or two lines of code change. Okay, and the programs remain functionally correct. So to summarize, if there is one thing that you wanted to get out of this talk is that the quality of the GPU software matters because software affects our life. And if you have reliability issues, like sometimes the software misbehaves, then that affects a lot of things. And since there is a lot of software today is using GPUs, and programming GPUs is particularly hard, you need actually tools to help improve that reliability of the GPU software. Tools means like the software tools I'm talking about here. Also, this is a kind of a cat and mouse game because what we have been finding is that every time NVIDIA introduces and also AMD introduces new programming features, there are new types of bugs that can actually pop up. So it's kind of a continuing one. So we have multiple submissions also under this topic. Also, the other side of the coin is performance bug. When the program is functionally correct, but it is not using the hardware in the most efficient way. And given the GPUs are how costly they are, any underinflation is a lot of dollars left on the table. So, and those can be subtle too. So you need software tools to detect those, inefficient programs as well. Okay? And this is the two parts, like the reliability and the efficient programming. These are the two parts of the quality of the software that we talk about, and particularly in the context of the GPU software technique. Okay, so that's the summary of the talk. And before I actually end, I'm ending it a little bit early. I can take questions. Like the actual work is not is done by students. These are mostly the PhD students. There are few master students as well in the lab who does the real job, so that I can actually come here and give the talk. Okay, with that, if you have any questions, I'll be happy to take, or if you want me to get into any of the details, I'll be happy to explain. Yes, go ahead.
Sir, when you were using Icrcicn, sir, does before that, sir, most of the race conditions were happening on the CPU itself, sir. Sir, however, do you think, sir, using Icrcicn on GPU parallel and alongside the GPU kernels, like introducing parallelism on the GPU kernel, sir, does that increase the utilization of the GPU which could have been better used by the models which are already running on the system?
I didn't get your question. Can you say it again?
So my question is that, sir, when we are using Icrcicn, sir, before Icrcicn, most of the race conditions were on the CPU, sir, on the CPU side.
No, there's a completely different thing. So in the CPU also, any parallel software can have these conditions, right? So during the 2005-6 to 2010, when the multi-threaded programming started coming, there was a lot of research on how the multi-threaded different threads can actually race. But those type of races are very different from the things that actually happens on the GPUs. Although, philosophically same, but like for example, there is this unique things that the GPUs have that I was mentioning of the scope synchronization that doesn't exist in CPUs. So those kind of races cannot actually happen on the CPU. Similarly, this lockstep execution and so on, barrier execution and so on, that doesn't happen. That kind of concept doesn't exist on the CPU. So these are very specific to GPU programs, not applicable to the CPUs.
Okay, thank you.
Right.
Sir, my question is that since you are using software to increase the efficiency of the performance, now the hardware architecture that is underlying, so that is fixed, the connections and architecture is fixed. So is there a saturation point where you reach with the software that this much performance you can reach in efficiency, or is the hardware is not the limit? You can actually optimize the software more to increase the performance.
If I understand correctly, so basically, at the end of the day, we are not looking to change the hardware. So given a hardware, how well that hardware can be used with the software, that is what we are actually looking for. And in that context, what we found is that sometimes there are programs which are inefficiently written, which were actually having this extra synchronization and so on. Because of that, you can get the same output, but the program is just slower, unnecessarily slower, right? So those are the opportunities we actually figure out with this software tool we have. So it takes a program that you might have actually written, and then it actually outputs like what are the cases wherever you are actually leaving the performance on the table.
My question is, are you guys maintaining the software? I mean, as you said, as new version of CUDA they are using.
No. We don't. So with the new version of the CUDA, the type of races we are detecting or the type of bugs that we are detecting doesn't change. So this is targeting one type, and that actually works for that particular type of bugs that it is targeting. What we do is that as we discover new types of bugs and so on, both reliability issues as well as performance bugs, we create new tools for targeting those.
So you are basically maintaining the software.
No.
Yeah, so
Not
means like
may I also?
yeah.
Actually, back in 2010, when Red Hat released their RHEL 6, that time you can't format your boot partition with XFS format, right? So we detected that bug, we report it to Red Hat. Red Hat acknowledged it in their website, and then RHEL 7 they just remove that bug. Similarly, what they are doing if this is the stable release version, they are working with their Icrcicn and they are finding any bugs, then they are reporting and they are trying to channelize how so many bugs are there, how can we detect all more bugs on that particular release. They are not maintaining that CUDA release. CUDA release is available.
No, I am not.
Icrcicn is maintaining by them.
I am asking about Icrcicn.
Icrcicn is maintaining by them.
I am asking about Icrcicn.
Icrcicn.
Are they maintaining the Icrcicn as long as throughout the CUDA life?
Right.
They are maintaining it.
And we don't completely actually do that. If there is somebody actually asks for it, most of the times this should actually unless you use some very whatever you say APIs which are they are deprecating. Only then these things would not actually work. But we do not actually use any of those. So it actually works for what it works on. It's not really the CUDA runtime it actually depends on. It actually works on your CUDA program. That is what it actually takes in. So it doesn't have that tight integration with the particular CUDA release. It doesn't matter to it. Okay.
I have
Yeah.
one question.
Yes, correct.
We teach, it may not be related to your topic, but then while teaching programming language till now in the colleges like us, we mainly stress on CPU programming, the programming which you had done in 2005 maybe. But the age has changed to GPU. What specific changes should we adopt in the programming language teaching that it gets it can be used in the GPU programming also?
So GPUs are programmed very differently than the CPUs. So there is no way, it can be extrapolated from a multi-threaded CPU program. The best way to do is to go step by step. One should actually have basic programming, which is like sequential programming, and there should be a parallel programming course, which initially could talk about just the multi-threaded CPU programming, which could be like P-threads or OpenMP, two versions. And then there should be a portion where start talking about the SIMD extension of the CPUs, SIMD extension like MX instructions and so on, which are actually vector instructions. And then that starts actually building, then one has to actually jump to the GPUs. Once you jump to the GPUs, there's a very different programming, hierarchy programming methodology. So it doesn't extrapolate from how the CPUs are programmed. Although the CUDA is actually C++ dialect,
Yeah.
but the programming model is very different. Yeah.
So actually, we are doing some research work on current days artificial intelligence and machine learning things. So, sir, my question is that someone who is using a dedicated GPU in their system, and there are some programmers or some researchers who work on different online platforms like Google Colab and all. So we don't have that much money right now. We use the Google Colab features for the GPU and GPU purposes. So, sir, could you please put some light on the topic that a dedicated GPU, its efficiency compared to the GPUs which are allotted from the Google Colab, are they the same, or like there are some fundamental differences in it?
So two things, like what kind of GPUs they are actually giving, I don't know. Okay, so they are based on the generations. There's quite a different, just like if you buy an older CPU versus newer CPU, there can be a significant difference, not only performance but also in terms of features. Now, whether you have an, for example, in our lab we have absolute top of the class GPUs, but those we recently bought something that just in the lab, like it costs like 70 to 80 lakhs rupees a single server, right? But if you go into the cloud, the other thing that actually happens, that can happen is interference. So if in the cloud vendors, they make money by allowing multiple tenants, multiple clients to share the resource. Once they start doing that, there will be actually interference because somebody else is also running things. So that can impact performance. That is not, if you have a dedicated server, that is controllable. In the cloud, it is not in your hand.
Sir, I have one more question, sir. Sir, nowadays we see that NVIDIA is becoming the key player in this part of GPU programming and all. And as you also said that there is another company named AMD which is also working. So, sir, can you please inform me or discuss about that AMD is not able to reach that much, but NVIDIA is reaching out to the bigger, larger aspects of customers and other things. So what might be the reason behind it? Is it only due to the technology part or some other aspects are also behind it?
It's mostly the software lock. AMD's GPUs, the hardware is not bad. Their problem is their software stack. And NVIDIA has so many closed-sourced libraries. People actually relies on them over the time. There is no technical thing as such, but it's more of what software lock that they have.
About the optimization and all those things.
Yeah, they have also had much better tools debugging tools and so on compared to say what you get from AMD.
So what is the status of Intel now with GPUs?
Is useless.
That's why Suvarna is question.
Intel GPUs are, even the AMD seeded our lab with a bunch of their top of the class like GPUs. Gave large servers for free. None of my students are ready to use them. They are all on the NVIDIA GPUs.
Yeah, one more thing.
Yeah.
What is the last question from the audience? If anybody is not there, what means any free courses or open source courses which you can recommend for GPU programming?
One thing that NVIDIA does, and which is part of this log, is that they have a huge set of really nice video lectures. Those are not bad, not bad. So they do a little bit of too much of marketing along with that. So that is something that needs to be filtered out. But other than that, it's just actually pretty well-made videos. There is one that is particularly good. They actually made set of lectures for one of the US national labs, and it is on their website. It's pretty good.
DLI workshop also freely available.
Which one?
DLI, Deep Learning Institute, that course. That is also from CUDA NVIDIA. DLI also. And free certifications they are given for all these courses.
Sir, I have a question. How is programming in a dedicated GPU different from an integrated GPU which we have in a CPU? Like how much different is it?
Yeah. So it's not dedicated GPU, it's actually, we call it a discrete GPU and an integrated GPU. So for all the heavy computing, you use the discrete GPUs. So what is the difference? So in an integrated GPU, it comes with the CPU in the same chip. It's actually a small GPU. Typically used only for driving your graphics. For example, in your laptop, you will have CPUs with an integrated GPU attached to it. For heavy computing, those are not good enough. So that's why the discrete GPUs come in, where the motherboard, they are connected from the CPU with the PCI slots, the PCI, and the basic difference is that they are just much bigger, and they also have a dedicated onboard memory, high bandwidth memories, which the integrated GPU do not have. Otherwise, the programming and so on, they can be programmed with the CUDA and so on, same thing. No other difference.
And also I have another thing, like how can I as an undergraduate student code some simple things like without using those PyTorch or TensorFlow's APIs, like code some simple things and do some simple calculations like linear algebra and so on in a dedicated GPU, like NVIDIA GPU chip comes in a laptop with this.
Yeah, you can do that.
Yeah, like
This is possible to do. Like you just install NVIDIA runtime and you will be able to do that. Even the GPUs, some of the gaming laptops will have a discrete GPU on them. So, yeah, we can do that. It's like, in our courses, when we actually give programming assignment on the GPUs, so we have a bunch of them on the, for the students to use for the teaching. But some of the students actually use their laptop GPUs as well for doing the CUDA program.
So does that impact the performance? Like for a computer hardware, the GPUs are generally bigger in size and they have
There will be performance difference. But for programming assignment, that is not the thing, because the way that we evaluate that, we take the program, we run it on our GPUs in our lab. The TS will evaluate, right? So it doesn't matter whatever they are programming.
So I hope there will be no more questions. So thank you, sir, for such a wonderful, informative and interactive session. So a big round of applause for sir. I would like to give a small token of appreciation from our side.
So, those authors who have technical sessions can go to the sessions. The session will start. Oh, here on my. চলে যাবে?
হ্যাঁ আমার বইটা ভালো লাগে।
ঠিক আছে। আমি তাহলে পরে কথা বলবো। হ্যাঁ, স্যারের ব্যাগটাগুলো দাও। হ্যাঁ, যাও। স্ক্রিনটা একটু অন রাখো, সৌজন্য।
হ্যাঁ, স্ক্রিন অন রাখবো।
স্ক্রিনটা অন রাখো। ব্যাকগ্রাউন্ড স্ক্রিনটা একটু অন রাখো।
হ্যাঁ হ্যাঁ, আসা হচ্ছে।
দু একটা প্রেজেন্টেশন বাকি আছে। হ্যাঁ, ওই আমার তো স্যার হ্যাঁ,